All right, so for our last video, we're going to actually look at a pretty famous application of the dot product, and that's basically to help us find the angle between two vectors. So let me give you a really quick sketch and give you a basic idea of what's going on. And so let's just say we have a vector u, all right? And then we have another vector, the vector v, right? So we've got the vector u has coordinates a, b, and the vector v has coordinates c, d. What we're looking for is that angle right there, right? The angle between the two vectors. And it turns out that if we basically considered u minus v, all right, we'd end up with this vector right there, right? And that's really important because what that allows us to do, right, is apply the angle that we have is the opposite of whatever that side is, right? And that's basically u minus v. So if I can find the magnitude of that and the magnitude of u and the magnitude of v, what I essentially have is the law of cosines. All right, and so the law of cosines, going from what we had, basically says that this side, right, if I take that side and square it, and then that would equal to one of the other sides squared plus the other side squared minus 2, one side multiplied to the other side, cosine of theta. And so basically we have found a way, right, the angle that I need, we now have it in relation to the u's and all that other good stuff. All right, so that's basically the idea that we have going forward. All right, and so what we end up getting then, right, is this and this. Let me just kind of piece things together. If we guys are really interested in the formal proof, I'll really put it together. But this, right, basically becomes u minus v dotted with itself. And this becomes u dotted with itself. And this becomes v dotted with itself. So we just saw that in some properties that we just discussed. All right, and then here's where the math gets a little messy with the A's and the B's and the C's. So I don't want to bog us down. We're already well into this module, and I think you guys are a little tired. But when you do all that math right there, when you actually perform those little dot products with all the variables, amazingly, what you end up with, the result of all this, is that the cosine of theta is equal to u dotted with v all over the magnitude of u and the magnitude of v. All right, so you can kind of see there's going to be a 2 that comes along, right? We're going to end up dividing by their magnitudes to get the cosine by itself. But all that train wreck turns into basically u dotted with v. Pretty amazing, and like I said, in class, if you guys are really interested, I'll do a formal proof for you guys. But right now, I'd rather just cut to the chase and start using that. So there's basically our formula for how to find the angle between two vectors. All right, so let me go ahead and do the first example then. So with our first example, we got the vector v is 3, 4, and the vector u is -1, 2. So in order to find the angle between these two guys, I definitely need to find their magnitudes and I need to find their dot product. And then we basically take the cosine of that. So the dot product here, right, would be 3, 4, dotted with -1, 2. So we end up with -3 plus 8. We end up with 5. The magnitude of u, right, this was u dotted with v. The magnitude of u would be 3 squared plus 4 squared square root. And so that ends up being the square root of 25. That also is 5. And the magnitude of v is the square root of -1 squared plus 2 squared. All right, and then so when we put all that together, right? This gives us the square root of 5, alrighty? And so what we end up having then is that the cosine of theta is equal to my dot product, 5, over the magnitude of each one of these dudes. There's a cancelization, but to cut to the chase, I'm basically, the angle that I'm looking for, right, is the inverse cosine of 1 over the square root of 5. And I'm not going to bother rationalizing the denominator in this case, right, because we're just trying to find the angle there. So when I go to my Desmos, right, I'm digging it out, right? So when I go to the Desmos here and do the inverse cosine of 1 divided by the square root of 5, what I end up finding is that theta is 63, looks like 43, 49, 43 and 49 degrees. So if I was to line these guys up, right, so -1, 2, so here's the angle V, and then 1, 2, 3, 1, 2, 3, 4, right, there's the angle U. That angle right there is 63.4349 degrees. So that's basically the application, right? So like I said, I just kind of want to use it. So in the next one, right, I got V times W, right? And so in this case, we got to find what's their dot product. As a matter of fact, it doesn't matter order, right? You can go V dotted with U or W dotted with V. We know it's commutative. But in this case, we have -3, -1, dotted with -2, 1. So we end up with 6 plus -1. I also end up with 5 there. The magnitude of V is -3 squared plus -1 squared square root. And that's basically the square root of 10. And the magnitude of W is -2 squared and 1 squared square root. And it looks like it's the square root of 5. So the cosine of the angle between these two, right, is the dot product 5, right, divided by the square root of 10 square root of 5. And so theta is basically the inverse cosine of 5 over the square root of 50, right? And we could probably simplify that and all that other good stuff, but I'm just going to go ahead and just type it in the way I've got it. And what I end up getting is that theta is equal to 45 degrees. All right, so again, if we were to draw a picture of this real quick, you got -3 and -1, right? So there's one vector. And then we got -2 and 1, there's the other vector, right? That angle between them is 45 degrees, right? And then last but not least, right, for my next two vectors, again, just kind of following the MO, we gotta basically find their dot product. So in this case, we have 3 and 2 and 4 and -6. And so we get 24, right, plus -12. And what we get there is 12. All right. And then if we found the magnitude of V, that's 3 squared plus 2 squared. I think that's 9, the square root of 13. And the magnitude of W is 4 squared plus -6 squared square root. That's 16 plus 36. What is that? The square root of 52, right? Which again, probably can be simplified, but I'm just gonna leave it as is. And so what we end up with is the cosine of the angle between them, right, is basically going to be, oops, you know what? I made a mistake. 3 times 4, I knew something was wrong here, right? This should be 12. And so we actually get a 0 there. So we end up with 0 over the square root of 13 and the square root of 52. I'm sorry about that. And so 0 divided by anything, we're basically looking at the cosine of 0. And of course, I think we all know what value does that. It's 0 degrees. So this basically means that these guys are parallel. right? And if you drew that, right, we have 1, 2, 3, 1, 2, and then we have 4, excuse me, there. I'm really messing this up. 90 degrees, right? The cosine of theta is 0 if theta is equal to 90 degrees. So they're not parallel, they're perpendicular. My goodness, I guess I'm getting tired too, right? And so when we align this up, we have -4, 1, 2, 3, 4, 5, 6 down here, right? So the angle between them, that's a nice perfect 90-degree angle. So I apologize for that. So I messed up with my multiplication there, right? So the dot product ends up equaling 0, right? And so what this basically means is I shared with you guys, the dot product is how much one vector is acting along the other. Well, if they're perpendicular to each other, neither vector is acting in the direction of the other. So that's why we got 0 there, right? Which means that the angle between them is 90 degrees, right? And for some reason I'm thinking sine. All right, so there's basically your application. Like I said, if you guys are very interested in the proof of how all this mess becomes this, I'll be more than happy to show you that in class. But for now, just know that formula, right? Be able to use that formula because it does with regards to projections and things like that you're going to see later on in your math careers and physics careers, right? That angle between two vectors will be very important. All right, so that wraps up 7.4, and we're going to move forward and keep on trucking. Talk to you guys later.